Hello, this is Mr. Pruitt, and today I'm going to be talking about position versus time graphs. And this is the first in a three-part series that will have about different types of kinematic graphs. So let's start by reviewing what we've been doing in class the last couple of days. The first thing is that you need to remember that kinematics is the study of describing motion, and it's a branch of physics where all we focus on is how we describe motion. And there are six ways to describe motion that we've identified in class. One of them is by its position. Uh, that's where it's actually located. By the distance it traveled, how far it went. By its displacement, how far, where it is in relation to some origin point that we started with. The direction of its movement, how fast it's moving, and how fast its speed is changing. So all of these six ways to describe motion can be indicated on the position versus time graph. Much like the position versus time graph that we constructed in class last Thursday and Friday. Alright, so a position versus time graph, what it does is it plots an object's position, or its actual location, versus some amount of elapsed time. And what I'd like you to do is just go ahead and stop the video for just a second and plot the points on the T chart over here to the right on your note sheet. And then when you're done, connect those dots. When you're done plotting those data points, uh, go ahead and um, connect the dots up. All right, so everybody's back with me now, and you should have a graph, and it should have a general shape that looks like this one. All right. Now, what you need to know about this graph, the really basic things that you need to know about this graph is that first, each point on this graph represents the actual physical location, that's its position, of the object relative to the origin. All right, now, if you look at this graph, normally we would call the origin the 0 point, and we didn't, on this one, whatever this object is, I think that we're talking about maybe a radio control car or something like this. It was actually in a position, it actually started in a position that was 10 meters beyond the origin in the positive direction. All right, so this car started 10 meters away from whatever that starting position, that 0 position that we've established, and then over the next 10 seconds, as we drove the little car around, the car moved to a new position that was 10 meters away. Uh, 10 meters away from there was an additional 10 meters away from the original point. So at this point, uh, this this car is about 20 meters from the origin, even though it has only moved a distance of 10 meters. Now, remember that in physics, signs are generally used to express direction. So if you see -8 meters, that doesn't mean that you know we that we went that we measured out something in negative space. What we've actually done is we've said that from whatever origin point that we established, we are 8 meters um, to the left or down from that. And the signs are generally, since we usually use signs like positive and negative, the conventional way of looking at it is that up and to the right are conventionally positive. That means that when we talk about going up, we're going to say that's a positive direction, or when we talk about going to the right, we're going to say that's a positive direction. And when we talk about moving downward, or when we talk about moving to the left, that's negative direction. And we can tell that from the graph. Whenever we see positive slope, then we know on a position versus time graph, positive slope lets us know that that object is moving in the positive direction. And going the other way, we know that if we see a negative slope, or one that's going down and to the right, then the object is moving in the negative direction. So what can we tell from the shape of the graph? Well, position versus time graphs really come in three shapes. They come basically in a curvilinear shape like this. or they might come in a linear. They might come in a line that shows some kind of upward or downward progression over time, having a non-zero slope, or we might see a flat line that has a zero slope. So when we see this curved line, uh, that's an indicator to us that the object that we're looking at, the graph that we're looking at, the object that's been measured, is accelerating, that it's changing speed. In this case, the it's changing speed very quickly. We can see that it's accelerating in the positive direction very quickly. Now, if the graph is linear and it's not curved like this, if it has a non-zero linear slope, then we can say that the object is moving at constant speed. So what we're saying is that from this point, from this position here to this position here, it is moving the same average speed all the time. And then the final one would be if we had something like this where the graph had a slope that was equal to zero, then the object would be at rest or not moving. All right, so what does the slope of these lines tell us? Well, um, besides telling us direction, because remember that positive slope tells us direction and negative slope tells us negative direction. The actual slope of the line of each line segment can tell us something about the object's speed. In fact, each line segment represents the object's average speed during that part of its trip. Now, one of the really things that's important to remember about this is that as the slope gets steeper, the faster the object's moving. Now, remember, when we talk about using signs, that's a convention that just tells us direction. So, since these signs only indicate direction, this also works for objects moving in the negative direction. So this one is moving slowly in the negative direction. If we had a steeper slope here in the negative direction, it would just be moving faster in that direction. Now, if you need a refresher on how to calculate slope, remember that slope m is equal to y2 minus y1 over x2 minus x1. And what we're really looking at here are ordered pairs of y2 and x2 and y1 and x1. So if we were looking at this from 10 to 20 seconds, well, we know that this point is at 2040, and this one is at 1020. And so if I took the second y, the ending point of 40, and I subtracted it from the beginning type point of 20, and then I took the ending time 20 and subtracted it from the beginning time 10, I would end up with 20 over 10, which would give me, when I divide that out, that would be 2 or 2 meters per second, which is the way that we would express this measurement. Anyway, I hope that you learned something from this, or that it's a good review. And we'll be using this tomorrow in class. So make sure that you have it and that it's ready, and that if you there's some part of this you don't understand, be ready with your questions when we get here. Thank you and bye.